Hey, what's up everybody? It is Mr. Boylan, and in this video, what in the heck are we gonna do? We are gonna use thermochemical equations to calculate energy changes that occur in chemical reactions and classify those reactions as exothermic or endothermic. As always, breaking it down. And numero 4, we are going to then calculate the enthalpy change of a reaction from enthalpies of formation. Okay, so the next thing we're going to talk about is how can we determine what the enthalpy change is. We are going to use a formula that is provided to you on your formula chart, and you can determine the enthalpy change simply by summing together the heats of formation of your products, summing together the heats of formation of your reactants, and then subtracting the heats of formation of reactants from the heats of formation of your products. Basically, it would be really insane to make a list of the heats of reaction for all chemical reactions, since there's a lot of them. So instead, what scientists have done is simply record the standard enthalpy of formation for a compound. Now, there are still a heck of a lot of compounds out there, so you have to look at a pretty extensive list. But hopefully you can imagine how more intense the list would be if we were to make a list of just all possible reactions. Now, these standard enthalpies or heats of formation are simply defined as the change in enthalpy that accompanies the formation of 1 mole of the compound in its standard state from its elements in their standard states. So as you take a look at your screen, we've got the formation of 1 mole of methane gas from its elements in their standard states. You also have an example there of the formation of 1 mole of sulfur trioxide gas from its elements, sulfur and oxygen. Couple quick things about heats of formation. Recognize that for comparison purposes, we are going to sometimes see fractional coefficients to ensure that we have only 1 mole of our compound formed. So as we come back to this, again, simply note that by definition, heat of formation is the formation of 1 mole of a compound from its elements. And so sometimes you're gonna have to adjust your coefficients so we get the formation of just 1 mole. Notice the fractional coefficient here. And the second thing to keep in mind about heats of formation is that recognize for elements in their standard state, it's always 0 kilojoules, as they're used as the reference as the heats of formation of the compounds. So as you spend your weekend studying a list of heats of formation, that anytime we come across an element in its standard state, its heat of formation is 0. Okay, now it's also important as you work to determine the enthalpies of heats or heats of reaction, that you are sometimes going to encounter a variety of subscripts following your delta H. Don't freak out. It just means that you are going to calculate the enthalpy change for a specific type of reaction or change of state. So some common examples that you're going to see are delta H of combustion, delta H of neutralization, delta H of solution, vaporization, fusion. All of these things are calculating heats or enthalpies of reaction. But now we're just talking about a specific type of reaction, like a combustion reaction. And also, don't get thrown off by that little naught symbol. It simply indicates that we're under standard conditions, 1 atmosphere and 0 degrees Celsius. 273 Kelvin. Whew, okay, and the final thing that you need to take away for today's video is the idea of energy profiles. And these are just diagrams that show us the theoretical representation of the energy pathway as the reactants are turned into products, as your reaction progresses. And so you're going to have to interpret diagrams or profiles that look sort of like what you see on your screen there. Now, some things to keep in mind. 1, the enthalpy change can be determined, again, simply by comparing the energy of the products to the reactants. And as you look at the 2 diagrams that you have in your notes, the exothermic reaction, the energy of the products is less than the energy of the reactants. When we solve for the enthalpy of reaction, it's products minus reactants. And when your product's value is less than your reactant's value, you're going to end up with a negative enthalpy change. And again, the negative just means exothermic, that it's been released. Conversely, if you think about your endothermic reaction, note the products have higher energy than your reactants do. And in order to make that happen, you have to have added energy. So it's an endothermic process. Coming back to this equation, when the energy of your products is greater than the energy of your reactants, you're going to get a positive delta H. And the last thing to take away is just recognize that activation energy is the minimum amount of energy the reactants must possess for the reaction to proceed. And so many times in these reaction profiles or these energy diagrams, you're going to see these little humps. And we'll talk a lot more about activation energy when we get to kinetics. But simply recognize that in order for you And for many reactions, in order to go from reactants to your products, you have to put a little bit of energy in order to get that reaction to happen. A great example would be to think of a combustion reaction. Many times, you've got gasoline, which is really, really flammable, but it's not going to just combust without some sort of input of energy, a spark, a match, some sort of activation energy to get that reaction to proceed. Okay, and that's it for today's video. Check out some of the references beneath the video for some great times.